Hello everyone, good morning, good afternoon, and good evening. I am Abhishek Sengupta, staff data scientist at Walmart, and today I am going to be talking about our work that me, alongside with Biswajit Pal, Director Data Engineering Tata Click, and Shubhadeep Moitra, Senior Data Scientist at Walmart, have developed. So essentially, we are going to be talking about intermittent demand forecasting in scale using a meta modeling framework, which we have achieved via a deep auto-regressive linear dynamic system. So let me tell you a bit about the problem statement that we're trying to solve here. So as you know that Walmart is a retail company, and reliable demand forecasts of items, that how accurately can you forecast what the demand or the sales of a particular item will be. So reliable forecasts of these are very essential and integral to the health of any retail operation. So because accurate forecasts will lead to improved decision making and outcomes throughout the entire planning horizon in terms of replenishment, capacity, and also resource planning. So if I just double click on that, so what we essentially have in Walmart, per se any retail organization, is that we have a planning horizon and we divide that horizon into short-term goals, mid-term goals, and long-term goals, right? So short-term goals generally range from 0 to 14 days, and if we have accurate demand forecasts, we can use those for short-term planning in terms of store replenishment, as in what items to bring into the stores, what items to replenish in the stores, inventory allocations, how to optimize inventory allocation in this sense. And now if we slightly broaden the planning window to say 2 to 8 weeks, so then also demand forecasting plays a huge role in capacity management, promotions, and markdowns. So for example, if I talk about promotions and markdowns, so suppose I know beforehand that the sales of a particular item X will say decline in the next 3 months. Then what do I do to bring up the sales? So shall I promote that item? Shall I give high discounts of the item and so on, right? And if we further extend our planning horizon to say over a period of 1 year, so here again accurate forecasts can help us in assortment planning, in space optimization, as in how to arrange your items in the store, what is the optimal assortment that will increase your sales, and so on. So as you understand that reliable and accurate and also robust demand forecasts are very, very, very crucial for any planning throughout the entire product life cycle, right? Delving a bit deeper into this, so as we know that forecasting models can be developed in different levels of granularity. So what do I mean by granularity? So for example, you can do a prediction of sales at a department level or a category level or an item level. So here I have mentioned SKU. So SKU stands for item essentially. So what I'm trying to say is that you can have demand predictions so you can predict the demand, for example, say what is the number of bananas what is the total amount of sales that bananas will have in the upcoming weeks, or you can go one level higher saying that what is the total amount of sales that the entire fruits category will have, or even go one step higher saying that what is the sales that the entire department, which is produce department, will have, right? So you can predict at various different levels of granularity, right? The other level of granularity is at what level are you doing the prediction temporarily. So by temporal, I mean that you can either have weekly forecasts, you can have monthly forecasts, you can have year over year forecasts as well, right? And also there is another level of granularity which is geolocation specific. So for example, you can predict what will be the sales in a particular store, or you can say what will be the sales in a particular group of stores which are located say close to each other, which falls into the same region, right? So you can have all this different level of granularity in which you can do the predictions. Now it's intuitive that granular forecasts, that is at the very granular level, at an SKU week store level, they are much more valuable, right? So for example, if I tell you that I'm able to predict what will be the sales of bananas in the next say 10 to 12 weeks in a particular store, that will be much more valuable to you rather than saying that what will be the overall sales of fruits in the next month in this particular region, right? So the more granular is it, the more actionable these forecasts become. But the problem with granular forecasts essentially, and especially for certain categories of items, is that it leads to temporal intermittency. So what does that mean? I will just explain. So this is especially true for slow moving items, that items which do not have very high sales, they have low sales, they don't always sell, they sometimes sell, and all these. And these lead to prediction inaccuracies, right? So for example, we see a slow moving item's temporal pattern in this graph on the right. So for example, the graph that you see here, so you see that it's a zero inflated graph, right? So there are lots of zeros because there were lots of items which did not sell. So typically how you visualize these items is that you will have seemingly random sales in between with long spells of zero sales in the mid portions, right? So these are called zero inflated time series models, and these violates time series assumptions because number one, first of all, they are not stationary, and second of all, time series requires all the points to be continuous, and these are not continuous data points, right? And then because it's also inconsistent, the data, right? So it does not follow a typical cyclical pattern or a seasonal pattern, that the lumps that you see do not occur at regular intervals also. So that's why decomposition is not possible in this scenario, right? So you cannot do a time series decomposition here, right? And also the data is also lumpy in the sense that, I mean, it closely ties back to inconsistent. So it has the intermittency, right? So the period of zero sales, that also varies. Sometimes you will have 2 weeks of zero sales. Sometimes you will have as high as 6 to 7 weeks of zero sales, right? So all these problems combine together, and these lead to high prediction inaccuracies. So coming back to formalizing the entire problem statement that we have, so the demand forecasting patterns, first of all, can be broadly classified into the 4 broad categories which I have shown here, right? So the one on the bottom left, which is smooth, right, is perhaps the most easiest to forecast. So these are fast moving products which have a very smooth temporal pattern, as you can see here. So for example, fresh products, produce products, and so on. So they have a very smooth pattern and they're easy to predict. So there exist a lot of prediction algorithms and literature for these, such as smoothing algorithms, time series models like ARMA, and so on. And if it's very smooth, you can simply do with moving averages. So that alone suffices. Moving to the next one, which is, say, cyclic. So cyclic is, you see lumpiness here, but the lumpiness is periodic in the sense that the periods of the period of non-zero sales, they repeat themselves, right? So seasonal products such as seasonal fruits, back to school products, and so on. So you will see a seasonality or a seasonal pattern there. So what we can do here also is you can do a seasonal decomposition to get the seasonal patterns and then make a forecast. Also, time series models such as SARIMA, which is seasonal ARIMA, can also help here. Croston models are also specifically good in these cases, right? The third one is erratic, which is slightly difficult to predict because they seem random. The patterns may seem random, but these products are highly affected by exogenous factors, right? So there are a lot of other factors which affect the sales of these products. So if we can correctly identify those products and attribute the sales of these items to these features, right? So what we can do is that we can use those attributions to again accurately predict for these type of patterns. For example, electronics, home care, right? So let me take electronics as an example. So if you know that, say, there is a new launch of a new phone in the next month, so you would anticipate a very high sales in the couple of weeks following its launch, right? So if you don't take those things into account, you will see this seemingly erratic pattern, but considering those patterns into account or those features into account, you can easily predict for these items as well. So methods like regression, boosting models like XGBoost, tree-based models such as REMAX, which is ARIMA with an exogenous factor X. These are all especially helpful in predicting for these patterns where the products are affected by exogenous features. So this leaves out the intermittent time series pattern, which is in the top right here. So as I said that these patterns are observed for slow moving low demand products like say plants, medicines, home decor, and so on, right? So it is in this category that we do not have any traditional ML or time series approaches, right? So there are certain approaches that have been used to tackle intermittency, for example, thresholding, Croston, tree-based models, and so on. So they alleviate some of the inaccuracies for prediction of intermittent time series models, but they fail to capture this inherent lumpiness of the data. So what is causing this lumpiness is not accurately captured by these models. So what essentially happens is that for intermittent time series, as I say, the time series assumptions break, often leading to over forecast. So if you look at the graph at the bottom here, so here we have the actual values in orange and there are lots of zeros here. And the forecast, if you see in the places where it's 0 in actual, the forecasts have overshot. So you get a lot of over forecast in these cases. So recapping the problem at hand. So our problem is to devise a robust and accurate intermittent time series forecasting solution. And we have to build this at scale, because if you know the level at which Walmart operates, right, the sheer number of items that it deals with, and remember that we are making item store level forecast, right? So the item multiplied with the total number of stores, so that's a huge scale. So what we have to do is that we have to build this at scale, and we use around say 2 years of transaction history, which is around 10 million records. And also what we have to make sure that the entire forecasting solution runs within a stipulated time window. In this case, if it runs every week, we had a 10-hour window by which the model for each week should train and then run itself, right? So we only have a 10-hour window by which the forecasts should be generated, right? And also we should provide 14-week ahead forecasts for these items for all item store combinations. And one essential point here is that we should also provide forecasts for even new items which have very little transaction history. So the typical cold start problem, that how do you again forecast for items which do not have as rich a transaction history as other items, right? So we are tackling all these problems using a novel meta model architecture, which we have named as DEEP ARLDS, which stands for Deep Auto-Regressive Linear Dynamic System. So let's break down our meta model framework. So our Deep ARLDS module involves 3 key steps. First one is explicit feature engineering. So here we try to identify and select or elicit explicit features which explain part of the apparent randomness in sales. So we try to analyze and figure out that what are the possible factors that lead to the changing sales patterns, and what we try to do is that we try to just list them down and select the most important features out of them. The second part is implicit feature modeling, right? So you have captured all the explicit features which can possibly lead to the changing sales pattern, right? But there will be certain features, because again it's lumpy and there is apparent or inherent randomness in the data, so there will be latent features which we cannot capture in the naked eye. So these latent features will map the underlying stochastic distribution of the randomness, right? So this apparent randomness, can we attach a probability distribution to this, and then from there we extract some latent or hidden features, right? So this is achieved using a linear dynamic system. And the third part is a scalable deep learning model, which again employs a probabilistic model, incorporating both the explicit features in point 1, the implicit features in point 2. And this model should satisfy certain criterion. Number 1 is that it should learn complex temporal interactions by modeling the historical behavior of all the time series jointly. So jointly, number 1 will first of all speed up the process, and second of all, it will again try to alleviate the cold start problem for certain items which do not have much history, right? And secondly, it should be independent of traditional time series assumptions like stationarity, Gaussian noise, and so on. And thirdly, as I already mentioned, that it should have forecasts for items which have just started their product life cycle. So double clicking on each one of these, let me start with explicit feature engineering. So explicit feature engineering again involves 3 steps. So one is feature elicitation. So we first identify and list all possible features. In our case, it was over 300, which can explain variability in the series. So for example, price, promotions or markdowns, weather, store demographics, product life cycle, item attributes, calendar events, and so on. Now we possibly can't include all the 300 plus features. I mean, we can, but again, it will increase the cost complexity, training overhead, and so on. So what we do is that we try to find the feature importance. So here what we do is that we train a vanilla XGBoost with all the features, and then we evaluate the feature importance from Sharp plot. So I will not be going into details of what Sharp plots are, but essentially Sharp plots or Sharp values help us to determine the feature importance of each of the features. So now lastly, we select or we filter features out of all these 300 plus features. So we select features with overall highest importance. So the features that came out important for us were promotion markdown features, holidays, special events, temporal variables, right? So some time variables like day of the week, again we have week of the month, and so on, and they were Fourier transformed. And we use various item description embeddings, for example, the color of the item, the shape of the item, size of the item, and we used global vectors. Again, I won't be going into details of how glove works, but it essentially is a way to get text embeddings. And also the other variables that were important was time since the item or the store launched. So that is how we get the explicit feature list. Moving on to the implicit feature modeling, this is where things start to get interesting. So what we do is that we have the original actual sales YT, right? So this is my time series that we have, which is not regular. So what we do is that we train a linear dynamic system on the actual sales YT, and then we try to model the underlying hidden signals. So if you look carefully at this equation here, so we have the original values YT, which is my original sales or demand, and we are regressing YT against this ZT, and this ZT is what we call our latent or our hidden states. And we regress YT against ZT, and this ZT is again regressed with ZT minus 1, that is the hidden state value at the past time point. And also we have, this is another novelty of the work that we're doing, is that we have introduced a temporal difference variable called delta into the mix, right? And then we are simply training this model, and we are training, essentially what we're doing is that we're learning the parameters B, A, B, C, and so on to get estimates of these hidden values, ZTs, right? So now what is this temporal difference variable? The temporal difference variable essentially is the time interval between two non-zero sales instances. So essentially if you have a sales at week 1, then the item did not sell for week 2 and 3, and again the item sold at week 4. So my delta at week 4 will be 4 minus 1, which was the two non-zero sales instances, the difference between them, which is equal to 3. Now why are we doing this? So including delta in the state equation ensures that the state actually depends on the time instance at which the previous observation was made, right? So we know that what is the gap between two non-zero time instances, and we accordingly incorporate that into our model, right? And now the goal of this implicit feature modeling is again to get estimates of the hidden states ZT, right? So they are estimated using expectation maximization, and expectation maximization is done on Kalman smoothing and filtering equations. Again, these are details of how LDS works, so I won't be going into that. So essentially we are getting estimates of these hidden states ZTs, and these ZTs, or rather the estimates of them, denote the implicit features governing the stochastic randomness of the intermittency, right? So now finally coming to the deep learning model. So this is where the crux of the meta modeling structure is. So our meta model, so why is it meta? Because it combines the implicit features denoted by XT, implicit features denoted by ZT, which is obtained from the state space modeling, and then we combine these into a deep learning framework. So what the deep learning framework that we've used here is an auto-regressive recurrent neural network, or DPR architecture. And this is used to determine the posterior probability of the demand of the item with X's and Z's, my implicit and explicit features, as covariates, right? So what this, again, I won't be going into details of a deep AR architecture, but it essentially is similar to an encoder-decoder setup, but there is one subtle difference, is where that the same model architecture is used in the training and the prediction stages. so that it speeds up the model training. Right? So essentially what it's trying to do is that it's trying to model the conditional distribution, which is my predicted y's, as in my future y's, given my past y's, my past x's, which are my covariates, my past z's, and we are using this to model the future given the past, right? And here we are doing a simple decomposition by converting this into the conditional likelihoods, and then using multiplicative logic to write this as a product of likelihoods and so on. Again, I won't go in deep into the mathematics here. So what essentially we're trying to do is model this likelihood L, right? And this L, we are assuming it to be a negative binomial distribution because it's a zero inflated time series. So we are not using Gaussian, but we're using negative binomial. And the model parameters of this likelihood, so that is what we're training through this particular DPAR architecture. And the model parameters, again, is shared across all the SKUs within a category. So, and this is what enables forecasts for items with very low training history, because the model parameters are all shared. And now once we've obtained this posterior probability, right, of the future forecasts, what we need to do is that we need to draw samples from the posterior probability, right? So once we draw these samples from this posterior probability, what we need to do is that once we have enough samples, we take a sample quantile. In this case, we are taking the 0.75th percentile, and this is a representative of the final forecast that we have, right? So this is how the deep learning model works for us. Now, if I just go into a bit deep of how the deep ARLDS network architecture looks like, so you see the training architecture here, the prediction architecture here. So as I mentioned that at each step T, the network inputs are my explicit variables X, my implicit covariates Z, the target value at the previous time point Y, and also the previous network output, which is H T minus 1. So essentially we're using these to try to model the likelihood of Y given the model parameters. And then what we're doing is that we are training this model based on the training data that we have, that is the past data, to obtain likelihood estimates of the posterior. And then what we are essentially doing is that we are drawing samples from this posterior. So we are drawing Y hats from this posterior, and for prediction, what we're doing is that suppose we got the prediction for yt plus 1 as y hat t plus 1. So we are feeding that into this architecture to get a prediction at time point t. Let me rephrase that. So suppose we are getting the prediction at time point t minus 1 as y hat t minus 1. We are feeding that into the network architecture to get the prediction at time point t, which is y hat it. And again, we are feeding this back into the network architecture to get a prediction for y hat it plus 1. So essentially we are just propagating the repeated forecast that we're getting to get the continuous 14-week ahead forecast that we want. So this thing is getting repeated 14 times, right? And now, as I said, that once we repeat this process 14 times, we get one sample, right? So one sample containing all the 4 estimates. So now if we repeat this multiple times again, right? So it yields many samples from this joint predicted distribution, and we take the sample quantiles, as I mentioned, to be the 75th percentile of these many samples to get the final prediction. Now talking about how we handle scale here. So as I say, the data that we look at is huge, right? So we are taking a 2-year customer transaction history, which ranges to around 5 TB of data. And now how do we optimize this? So we have optimizations at various steps of the entire pipeline, starting from explicit feature engineering, wherein we're doing parallel processing in PySpark and code structuring through a 3 IDE. For implicit feature modeling, we are again doing a batch streaming in PySpark, and the EM algorithm in order to get the Kalman smoothing and filtering equations. So that is parallel processed using a cut and stitch or CAS algorithm. For the deep ARLDS, what we're doing is they are inputs and scale dependent parameters are scaled and descaled by the same factor to again speed up the training process so that it converges faster. And then instead of taking the samples of the sample outputs y hat t plus 1, y hat t plus 2, one at a time, we are using ancestral sampling to directly obtain the joint samples for the entire forecasting window. And also this entire thing is parallelized using GPUs. And finally, we're getting the demand forecast, a 14-week ahead forecasts, and we also have a model governance dashboard through Looker for quality checks, data and model drift detections. And because of all these optimizations in place, we have achieved a total runtime for all the 30,000 SKUs that we have. We have achieved, so the SLA for us was 10 hours. We have managed to do that in 7 hours per week. Coming to perhaps the most important slide, which is results. So as I said, the solution was scaled for 32 departments, which is around 30,000 SKUs across 210 Walmart stores for 14-week ahead forecasts. Now here we have compared that with some of the state-of-the-art models, right? So DPR-LDS is based on DPR, so obviously we had to compare it with DPR, then XGBoost. We also compared it with SariMax and Croston. So what we can see, so we have various error KPIs here. So for example, mean absolute deviation for zero as well as non-zero sales weeks. What is the SMAP or the symmetric mean absolute percentage error? What is my overfocus percentage? What is my underfocus percentage? So we have all these values listed here for each of the models. And we can see that DPR-LDS scores the lowest error metrics across all the KPIs, except perhaps for under forecasting. Although the total over forecast plus under forecast percentage is much less than all the other models, right? So herein we can also see the same fact illustrated through certain model examples, wherein for example, if we are doing a model comparison for say cartons, right? So we can see that the actual and the DPR-LDS forecast have almost coincided, right? Same men's sportwear here. So in conclusion, what we have done is that we have created a meta model architecture which allows for more accurate demand predictions at granular levels by successfully modeling the intermittency and the temporal interactions through linear dynamic systems and deep learning. And also we have managed to make the model more scalable due to parallel implementations using PySparks and GPUs. And also this model can be generalized for forecasting solutions where assumptions of typical time series modeling fail. So it need not be demand forecast always. It can be generalized to any forecasting solution where traditional assumptions of time series modeling fail. In the future, what we want to do and what we're currently working on is that further speed up DPR-LDS to achieve online live forecast. So sort of a real-time forecast if we can achieve with DPR-LDS. The second is add a segmentation module which allows for training multiple DPR-LDS model within the same category. Right now we have a single ARLDS for each category, but what we want to do is that we want to train multiple ARLDS within the same category so that we can capture within category varying item behavior as well. So that brings us to the end of this presentation. Thank you all.